And hello, welcome back. Welcome back to our discussion of the law of the wall, or rather, modeling the turbulence in the near wall region. So I'm not doing open form today, but this is very closely related, and you'll need to use it for fluid dynamics anyhow. But anyway, last time we were talking about the mixing length model, and we need an equation for L in terms of y plus. The question is how. So I'd like to turn your attention to the near wall region. Okay, so this was some notes I was scribbling. Just ignore that. I'll just do everything from scratch. Okay, so picture yourself near where we have that fluid ball near the wall, and it can travel some mixing length L before disintegrating. So what is the maximum L we can get, or rather what is the order of magnitude of this mixing length L? So when we are near the wall, let's say this is happening at some distance y from the wall. Well, it's kind of easy and intuitive to think that L has to be less than or equal to y. Okay, why is that so? Because if L is more than y, then if let's say this ball is traveling towards the wall, if for whatever reason it manages to hold its integrity, it will still break up, or it will lose its integrity at the wall. Alright, so L can only travel so far before the ball can only travel so far, this distance L, before it disintegrates. So it is usually somewhere along the distance from 0 to y where this ball will disintegrate. So L, because once it hits the wall, that's the hard upper limit, it will definitely disintegrate. So how can we put this inequality in an equation? So we can write L equals to some kappa into y, where this kappa is ranging from 0 to 1.0. Okay, so hopefully you get what I mean. So the fluid ball can only travel so far before disintegrating, and being so near the wall, the average distance it travels cannot be further than y, because when it hits the wall, it will disintegrate anyhow. And moreover, there are other factors near the wall, like this boundary layer, or the viscous, even you have a viscous boundary layer here even. So if the ball of fluid travels towards the wall and goes into this viscous boundary layer, there may be some mixing or whatever happening, I don't know. But the maximum it can travel is this distance y. That makes some intuitive sense, right? So that is the assumption we are going to go with. So we have L equals to kappa times y, where kappa is 0 to 1. Question is, what is kappa? How do we get this constant over here? So the constant over here, you have to do it experimentally. There's no choice in that. So experiments show that kappa is around 0.4, which is basically within our estimate of 0 to 1. So that's a simple part. So now that we have this, we can substitute this kappa y into this equation here, and we plug nu t back into our turbulent sublayer equation over here. So I substitute nu t with this equation, L squared du, or du bar dy, and that's what I'm doing here. I'm substituting nu t with this L squared du dy. Okay, so now that we have an expression in y, we can convert the y into a y plus. Okay, so I'll just copy and paste into here this L squared kappa y. So I'll substitute L as kappa y, and this is what the next equation is about. So all I've done is just to substitute L squared into kappa y squared. Nothing too big there. Next step, what are we supposed to do? We want to change all of this into the non-dimensional form. So y we want to change to y plus, u bar we want to change into u plus. So we can just write these two equations down. U bar equals to u plus times u star, and likewise y equals to y plus times y star. So we can just plug and play these equations in. U plus into here, u bar into here, and y plus y star into here. So I'm just doing that. So u plus, or rather du bar, is actually du plus into u star. Likewise, dy plus is dy into dy equals to dy plus into y star. That is the bottom denominator. And when we have a y here, we will just replace it with y star into y plus. So that was just copy and pasting into here. There's nothing too much of that. And after that, we can bring this out, and we get y square outside, y star square outside, and that will multiply into this u star over y star. So when you bring this out, when you bring this term out, you will have a y star square, right? You have a y star square, and that will cancel with the denominator here. Okay, that's why you have a y star u star. So what is y star u star? We have to go back. We have to go back into this equation here. Y star times u star equals the kinematic viscosity. So that's what we just substitute in there. Okay, so this is the expressions for u star and y star, and we find out conveniently that the kinematic viscosity appears in the numerator, and we can cancel with the kinematic viscosity inside the denominator. So this, okay, this should be u star y star here. Forgot. Okay, so after we do the cancellation, it is very simple. We have this du plus dy plus, and du plus dy plus here, and then the bottom is just the denominator is 1, so we are ending up with this expression, and we can just integrate this directly. I'll just skip the steps and just integrate it directly. We know that it's a logarithmic function. Okay, so we'll have 1 over kappa ln y plus y VSL minus 1 over kappa y plus VSL. What is this VSL here? Remember, this is we have two regimes, right? Okay, this is from the textbook after you integrate, so I'm not going to integrate. But remember, we have these two regimes. One is the viscous sublayer, where the natural viscosity is more than the turbulent viscosity, in fact much more. The other regime is where the turbulent viscosity is much more than the fluid kinematic viscosity. So this is the fully turbulent sublayer. So at a certain value of y plus, we will transition from the first regime, which is the viscous sublayer, into the second regime, which is the turbulent sublayer. Okay? So what is this characteristic y plus we are talking about? This will be the y plus of the viscous sublayer. So y plus VSL, or y plus viscous sublayer, equals the y plus where we transition from the viscous sublayer regime to the turbulent sublayer regime. Okay, let me scroll. Okay, so that's what we do. Of course, the other way to integrate is to just take square root of both sides, because the squares are here conveniently, and then we have a plus minus 1 into that will be equals to the right hand side here. And which root then should we take? Because we have a plus minus 1, we take the positive root, because, I mean, logically speaking, we should expect u plus to increase with y. So we will have positive values like so when we do this integration like that. And then again, we also get a logarithmic law, which is very similar to this. And we can see that over here, y plus VSL minus 1 over kappa ln y plus VSL. All of this is actually a constant, which we don't really have to worry about. Okay? So this is the proper limit of integration. Okay? So remember where we are transiting from the viscous sublayer to the fully turbulent sublayer. Okay? So where is this transition y plus? Okay, so where we have experiments that show, at least Prento and company, or Prento and Taylor, they did experiments before showing that at a y plus of more than 11.6, kappa equals 0.4. Okay, and this corresponds to the integration constants, the coefficients, a equals to 2.5 and b equals to 5.5. So this is all done by doing experimental data over various fluids, over various flow system. Okay, so this was after we non-dimensionalize everything, we can then fit experimental data in, and by fitting experimental data in, we get these coefficients. Okay, so the long story short is that we have in the boundary layer two regimes. One is the viscous sublayer and one is the turbulent sublayer. So in the viscous sublayer, we have a y plus of less than 11.6, and we will have this regime u plus equals to y plus. This is the viscous sublayer equation. Any more than that, then we will have a logarithmic regime here. U plus equals 2.5 ln y plus 5.5. This is also known as the law of the wall, or the log law of the wall. Okay, so we will have a sharp transition here from u plus equals y plus to u plus equals to some logarithm function of y plus, some linear log function. Okay, so this is how we fit the experimental data. This is how we fit the experimental data to find velocity profile inside a wall region, a near wall region. Because here the turbulent functions, turbulence isn't the same as the bulk fluid. So remember, when we have our K epsilon model, in the bulk fluid we will have this K epsilon model going on, but near the wall we will have to apply these wall functions, these near wall functions, in order to have an accurate representation of the velocity profile. Okay, so this is based on a model. Now, of course, if you don't want this sharp transition where we have two equations to describe this boundary layer, we can actually combine both of this into one kind of equation, and someone has actually done that before. So the person who actually combined both these laws into one equation, I think his name is Van Driest. Okay, I'll just write his name here, Van Driest. Okay, so this is the Van Driest model for near wall. Okay, oops. Okay, so basically, where does it come from? Remember, this was the original equation that we started with. Okay, so this is the original equation we started with, and so we have du dy. We expect it in this kind of form, 1 over 1 plus 1 over 1 plus nu t over nu. What is turbulent viscosity? We saw before. This is equals to here. Okay, remember, L squared into du dy, And then after, you know, doing the substitution, we have all of this here. So, okay, L squared du dy, we have the substitution in. Then we have non-dimensionalization. And then after that, we just get this kind of a formula. Okay, so we're going to copy and paste because this is just the turbulent viscosity. And then we can just put it down here. All right. So that is how we get this. Then of course we can do some changes here. Okay, so we can kind of have an equation in this sort of form. Okay. All right. So we can have an equation in this sort of form, but if we take a look at the Van Driest equation, all right, and of course you have to do a lot of manipulation just to get this du dy plus out of there. Yeah, so I'm not going to do that, but it's just to give you a comparison as to why the equation looks like it is, why the Van Driest equation looks the way it is, looks the way it does. So we take a look at the Van Driest model. So we have a du dy plus, du plus, dy plus, and that is equals to 2 over 1 plus, okay, you have a square root over here. You can imagine why there's a square root, because you have to multiply all sides by this, and then you have a quadratic equation in u plus du plus dy plus, because this is this times this will get a square, so you need to square root this. Okay, it's okay, squared. All right, and next thing you will have inside is 1 plus 4, this is going to be long, kappa square y plus squared. All right, so this is y plus squared, and then you'll have an exponential function inside. 1 minus exponential of y plus minus y plus divided by some constant a plus, all right, and this should be half, 1 over 2. Yeah, okay, and this term in the bracket is also squared. Okay, so hopefully you'll see where this ky plus came from. Okay, this ky plus came from here, and then this square root here probably, you know, it comes from the this term here. You see du dy plus, you have to bring it out, and then you have this square root thing. Okay, question is, where does this exponential term come from? Okay, because you see the ky plus in the denominator, etc., etc. That's fine. Yeah, but where does this exponential term come from? Well, remember our mixing length model over here. So remember we said that the maximum distance this thing can go, all right, this ball of fluid can go when it goes near the wall, it is some constant into the y value, all right, some constant times the distance of the ball from the wall, the fluid ball from the wall. Okay, L equals to kappa into y. If we just consider, you know, the hard wall limitation, that means you can only travel like the distance y before banging it into something. Okay, This is based on there's a physical wall, you will bang into something and then it will disintegrate. So wall limitation. Okay, but we have not discussed the effect of viscosity near the wall. So because you see near the wall we will have a viscous sublayer, and then we will have that effect kind of play into the mixing mechanisms. So there will be like okay, when we have a viscous sublayer, okay, let's say a viscous sublayer, this thing will actually act like a kind of a soft wall, right? Soft wall. So when this ball of fluid starts entering this viscous sublayer, then the velocity here is very slow, and it's almost like hitting a wall without hitting the actual wall. Because the fluid here is moving so slow, it kind of acts as a soft wall. Like, okay, yeah, it's a wall made of the fluid particles that are moving very slowly. So, yeah, so it will hit these fluid particles, and then these slow moving fluid particles can cause disintegration. So to account for these viscous effects, we actually modify the equation so that we have this. We have this effect. Instead of ky, we have some exponential function. 1 minus exponential minus y plus over a plus. Alright? And this is the Van Driest mixing length. Okay? Van Driest mixing length. Okay, Van Driest mixing length. So L is approximately k plus k kappa y into this exponential function. It must be some exponential function in order to represent, okay, I'm hitting a soft wall, I'm going to bang something, so but that something is not exactly the hard wall, but it's the viscous sublayer where there are slow moving fluid particles that pretty much act like a wall it pretty much acts like a wall. So the exponential term accounts for the viscous sublayer effects on mixing length. Okay, viscous sublayer effects on mixing length, or in fact you can just put the viscous effects. Okay, viscous effects on mixing length. Alright, so this is the Van Driest model, and this will actually give you a smooth transition from this viscous sublayer to the law of the log law region. Okay, let me put log law of the wall. Okay, I don't have a logarithm or something, but so this is pretty much it for the Van Driest model. If you want to take a look more at the law of the wall, you can just search it on Wikipedia, where you see this diagram here. Okay, and this diagram you see on Wikipedia, it's a very useful diagram. It will just tell you what we were discussing before. Alright, so this is what you can see on Wikipedia. You have this region where we have the log law. Okay, because this is a logarithmic plot against of u plus against y plus. You can see the logarithmic plots at the bottom. So u plus equals to y plus, that's the viscous sublayer equation. But you see, after a while, after somewhere, it stops working, and this is about y plus equals to 5. Then it starts deviating from the experimental data, which is in red. Okay, and the log law actually starts to kick in at around y plus equals to, let's say, 30. Yeah, 30. So in this region here, there is this buffer layer. Okay, and remember we were discussing this y plus equals 11.6 as a sharp transition to kind of approximate what's really going on. Okay, I didn't explain about the approximation before, but you can see this intersection between the log law and the u plus equals y plus happens at about 11.6. As you can see over here, this intersection here will be around 11.6 on this graph. But of course, you see there is a significant detraction from the actual experimental data. So this red line is best approximated by this Driest model, and that's what is being used in some CFD code. Okay, so yeah, this is not my image. You can find it on Wikipedia easily, but hopefully that gives you an idea of what's going on near the wall and why we have this kind of patterns going on. And just take note, yes, this is suitable for any K epsilon model where we have Reynolds average Navier-Stokes going on. So in the bulk fluid we have lots of turbulence going on, but near the wall we have to use this experimental data to model the velocity profile near the wall. Okay, so thanks for watching. I'll see you guys again. Bye bye.